the thing.
Looks like.
It was kind of graph, my favorite graph, 0.2 inches. So it's 10 to 20 times narrower than S, and it's a much different image than we can get, which is later.
How? Like what, how does that compare to a compare?
One angstrom is probably about what, the diameter of a hydrogen atom in that ballpark.
Probably 10 angstrom. No, an atom is about an angstrom.
Yeah, about an angstrom.
A hair is about a micron, so it's another 10 million times.
Oh,
Angstrom, 10 to the minus 10 meters.
okay, so going from visible to completely invisible. I see what you mean.
Okay, let's get started, and thanks for coming. I hope you're parked in parking structure 2, because that's where you won't get a ticket, or at least you shouldn't get a ticket. And if you do, don't pay it, just let me know.
So you do have some power around here.
No, I know, but I know people that have power. And
That's just as good.
so what I'm going to talk about tonight are, like a baseball game, hits and misses, interpretations of data that were correct and others that were incorrect. I'm not trying to humiliate anybody. Were they alive and still here? That's not the point. The point is that they were following the best evidence at hand. It turned out to be completely wrong.
Science.
That's science. I'll lead off with an anecdote by a magician and illusionist named James Randi, who's no longer with us. But he was a frequent guest on Johnny Carson way back in the day. And he was truly superb. But it annoyed him that people would come up and say, "Teach me how you do this magic." And he said, "It's not magic, it's a trick, right? It's an illusion. I have ways of doing this, but it's not magic. There's nothing supernatural about the way I do these tricks." And they didn't believe it. And so he became something of a debunker. He went around and debunked people like Uri Geller and so on. One day he got a letter from a fan. He said, "Mr. Randi, I have these special powers in my fingertips. When I go up to my fish tank and I touch the side of the fish tank, the fish scurry all around. And so I have this power in my fingers." And Randy thought it was just, frightened fish. And so he said, "Let's do an experiment." He said, "Put some opaque paper, wrap opaque paper around the fish tank and see what happens." And he forgot about it. About 2 weeks later, he got a letter back saying, "You're right. My powers can't penetrate opaque paper." Right? So no matter the lesson of this that I've taken away for many, many decades now is that even the most obvious data can be misinterpreted if you're in the wrong frame of mind. And so the first sort of misstep here is not a misstep. It's a success story. It's a home run, in fact, for 2 mathematicians. The discovery of Neptune. I'm going to move this before I end up splattered on the floor. Neptune's pretty big compared to the Earth. You would guess that it would have been easy to spot, but it's very, very far away. It requires at least a small telescope to spot. And the farther away you get from the sun, the slower moving you are against the stars. And so it becomes an exponentially difficult problem to detect these. This would be easy today. A planet like Neptune wouldn't escape a survey like the Vera Rubin survey or the SDSS or IRAS or any of those other venerable surveys that are meant to encompass the entire sky and look for things that move and things that change. That would be low-hanging fruit. And it would have been found eventually in a studied survey, but it wasn't. It was found in a different way. There were 2, and I hesitate to use the word astronomers. They were really mathematicians, but we count them as astronomers for their wonderful contributions to astronomy. Uranus had just been discovered about the time of the American Revolutionary War with George III by a German musician who was living in England named William Herschel. And Herschel discovered Uranus. He looked at because he was systematically looking at the skies, and he had the best telescopes. He made his own telescopes, and they were the best ones available on the planet. And when he looked at it, he knew right away that it wasn't just an out of focus blob, that in fact it was a disk. And he thought he had discovered a comet. he forwarded the information to the Royal Astronomer at Greenwich, just across the river Thames from London. And they watched it and calculated an orbit for it and said, no, we think you discovered a new planet. Of course, he was instantly infamous around the world. George III contributed vast resources to his astronomical research, not all of which paid off. But there you have it. He was a musician. He got sent here from Germany to get out of a war. His father didn't want him participating in the war, so he came, and he was a church organist. I played one or two of his pieces, and it's no loss to music that he took up astronomy. And so they said, well, what would make Uranus do these weird things? What do I mean by weird? It means like over in this part of the orbit, it's being pulled by an unseen planet that will eventually be known as Neptune, although the discoverer wanted to call it, name it after George III. But anyway, it's being pulled by this unseen planet. Nobody knows where it is, and nobody has seen it. And so in this part of the orbit, Uranus is just a little bit ahead where it should be in its orbit, not by very much, not something you and I would notice looking through a telescope, but by a few arc seconds. And this is really the beginning of precision astronomy. And when it moves, the closer you are to the sun, the faster you move. And Uranus then pulls out in front of this unknown planet. And now it's being pulled backwards. It's moving more slowly than it should. And it's behind in its orbit. And so these two mathematicians, Englishman and a Frenchman, independently had the notion of working the problem backwards using Newton's laws of gravity to hypothesize where would a planet have to be to cause these anomalous motions in the planet Uranus. And we have the two suspects here. On the left is Urbain Le Verrier, on the right, John Couch Adams. For a long time, it was argued who had the better claim on the discovery of Neptune. It turns out it was Le Verrier, but we didn't know that until relatively recently. The documents buried in the archives at Greenwich disappeared in the 1950s, and were only found in the things of an astronomer named Egan, who absconded with them. He just stole them, moved to Australia. And they found him in his belongings, and we were sorting it out after he died. And they said, holy cow, these are really important, and published them. And it seems like Adams was forever changing his positions where he thought the planet would be. Le Verrier was more confident, but we give them both credit for it. Le Verrier, of course, went to the Paris Observatory and said, I've worked out this position for a new planet. It must be there. Its gravity is giving itself away. It has to exist, and it's got to be in this little spot of sky here. It would be really great if you took some time to go look for it. And he was pawned off and said, we don't really have time for mathematicians here. We do astronomy. And he got sent away. A similar thing happened to John Couch Adams. Adams went to Greenwich to the Royal Astronomer and said, I worked out this thing where there's a planet, and we haven't seen it yet, but it's a new planet, and you would be the astronomer that discovered this brand new planet. And he said, that's basically the same thing. We don't do mathematics here, except that encompass in astronomy. And
they didn't have any graduate assistants.
They didn't have any graduate assistants to do it. Telescope time was hard to come by. Le Verrier got desperate. Being a French mathematician, he went to the Germans. And, the French and Germans get along historically like French and Germans. They just don't. And he went to the senior astronomer there in Berlin, Johanna Galle. And Galle had just received an updated set of maps that were far more precise and went far more fainter. You could see fainter stars in it. And Le Verrier was able to convince Galle through a letter that this was really something worth doing and that he should spend some telescope time looking for it. And he got his assistant together named D'Arrest, and they started looking for it, and it took about an hour. And that's all it took because the prediction was so precise. And instantly, Le Verrier on the continent was the discoverer of Neptune, and Adams was the discoverer if you happen to live in England.
Neither one of them discussed it. They just made predictions.
They made predictions, but nobody would have looked in that direction had it not been for them. And so this is a photocopy of inverse. It's I think it was actually black stars on white background, but it's the talks I give. I like to have the dark background, so you're not constantly being assaulted with bright light and then dark things like that. And the square and the circle are the difference of about 2 arc minutes. The moon's diameter, apparent diameter, is about 30 arc minutes. So this is very, very close. The predicted location and the actual location. Interestingly, at that time, Saturn was very near Neptune. They were essentially in what we call conjunction. This is what it would have looked like on the night of discovery in 1846. You see Neptune grouped very tightly with Saturn. This little asterism here is part of constellation Pisces. It's known as the circlet of Pisces. And if we went out tonight and looked well after midnight, you would see once again Neptune and Saturn are in conjunction with each other in the same direction, almost in the same direction in the sky, because here is the circlet of Pisces. And so the clockwork mechanism then of Newton, the universe was simply a machine that you wound up, and then it just kept repeating and doing the same thing over and over again, became established as sort of a gospel. Now, of course, we have probes that we can send out and send pictures. The only probe, and this is something of a miss, something of a small scandal. We've only had one probe to go past Uranus and Neptune. That was Voyager 2. And I sent back these stunningly beautiful images. The dark and the white clouds. The white clouds are like cirrus clouds on Earth. They're very high. They cast shadows. These are weather patterns, and they're not permanent. They change just like the weather patterns on the Earth. And this beautiful, nice close-up picture of the largest moon called Triton. It has, we've only seen 1/2 of part of it, because you can see the terminator, the other side is in darkness. And the flyby was so fast that we didn't have time to wait for it to rotate and see the other side. These are the fastest objects, among the fastest objects ever created by humans. The part at the top, the layer at the top, is nicknamed a cantaloupe because of obvious reasons it looks like a cantaloupe. What you see below is an example of what has become known as cryovolcanism, that even at a distance of 40 times the distance of the Earth from the Earth is from the sun, there are still little mini volcanoes of ice that spew out something akin to soot, and then get blown into those these little things here. Here's the source of the material, and there it is coming out, and they're all going in the same direction. This is also, I think, requires explanation yet.
Can you imagine being the first scientist looking at these images and going, what the heck?
Yeah, in fact, the professor here was at Caltech during this flyby, and for a completely different reason. He was one of the first people to see them come off the printer, the sublimation printer. Yeah. Switching gears, search for Vulcan. No, not the one with the other ones. The other one. Leverrier was coming off of a big high. He had garnered immense popularity and notoriety for predicting and then finding the planet became known as Neptune. And he started looking at other orbits. And look at the orbit of Mercury. Mercury goes around the sun every 88 days. It's pretty fast. And so studying its orbit, it's not a perfect circle. It's an ellipse. And it makes it ideal for looking at this sort of thing. This diagram on the right is very, very exaggerated. What we're talking about here is the ellipse has a long axis, and that long axis precesses, it rotates around. Not very much, about 500 arc seconds. I can't do that math in my head. about 9 arc minutes. Full moon is 30 arc minutes. In a century, it moves 9 arc minutes out from where it was. But the precision that was available, even in the 19th century, allows that to be apparent. That was a problem. Most of the precession, most of this change in the orbit orientation comes from gravity from Venus and Earth and Mars and even Jupiter. And when you add in all those effects, which back in the 19th century must have been extremely laborious, they didn't even have a calculator, right? Let alone a computer to do this. Working out these long strings of equations. And he could account for, of this 543 arc seconds per century, he could account for 500. But the last 43 arc seconds wouldn't go away. And Leverrier thought, well, what the heck? I discovered one planet. Why can't I discover another one? And so he hypothesized a planet inside the orbit of Mercury that was less mass than Mercury and very tiny, and that's why it hadn't been discovered, because people weren't looking hard enough for it. It was there, you just hadn't looked in the right place for long enough. And so I'm sure that when he looked at that and said, why not 2? Why can't I discover a second one? Now, every once in a while, about 13, 14 times a century, we can see Mercury from our position on Earth move in front of the sun. It's called a transit. And that affords very, very good position information. If you really want to know where Mercury is in the sky, when it's close to the sun, you can't see it because the sun's so bright. When it transits across the disk, then you get to fill in that information. And that would be one way, number 2 there on the list. The other way is to look at the environment of the sun, look around the sun during the brief minutes of solar eclipse. Now, we don't need a solar eclipse today. We have satellites to do that, little disks that come out and block the sun. The SOHO satellite is one. The new GOES weather satellites are going to have a side camera that looks at the sun because they're anticipating SOHO. SOHO's been up there for like 35 years or something. It's ridiculous. And it's the most amazing thing. But for 35 years, that team has been looking very closely at the environment around the sun. I've never seen another planet. Lots of little comets, thousands, 5,000, 6,000.
Those images all the time.
Yep. No, I do every day. That's my morning candy.
What is Mercury orbit on, let's say, at the close end?
Well, Mercury's orbit is about 40% the diameter of Earth's. I don't know what that works out to in miles or kilometers. Whatever 0.4 times 150 million kilometers. The difference between its perihelion and its aphelion is not that big. It's measurable, but it's when you look at an orbit of look at a display of the planets, it's not terribly obvious that Mercury's orbit is oblong. So these are the 2 strategies available to the 19th century. So in December of 1859, a country doctor in the place that I'm going to gamble is pronounced Orgeray, sent a letter to Leverrier saying that earlier in March, he saw something like the planet Leverrier was looking for that crossed the disk of the sun. This was 8, 9 months after the fact, and Leverrier hightailed it to Orgeray, which is still a very picturesque, I can't think of the word I want right now, very rural sort of place. It's not a big town. There's nothing really huge going on there. And he hightailed it there and interviewed the good doctor and said, are you kidding me? You had this information you didn't send me? Tell me, show me your notes. Show me the diagram that you made. He said, well, I don't really have paper. I've got this slate board over here that I mark on. And when it gets full, I just erase it. But I'm sure it was March. And I think there was a date involved. I think it was March 26th, 1859. And Leverrier sized him up and said, congratulations, we've discovered another planet. on the flimsiest of information, the flimsiest of data. Nobody would, a 10-year-old wouldn't be fooled by that kind of evidence. Nonetheless, that little meeting in central France kicked off a 50-year search for the planet that he named Vulcan, preemptively named it Vulcan after the god of the forge. We now know that Vulcan doesn't exist, and it cannot exist, because if it did, it would influence the orbit of Mercury in a way that would be unexpected, and that doesn't happen. The correct answer is that Mercury's orbit precesses because of a theory that Einstein created, published in his full form in 1915. The mathematical bits that hold together general relativity are brutal. Mathematics are brutal. But in concept, you can find places online.
And Einstein needed some help.
Einstein had to go to his friend Grossman, I think was his name, to help him with the
Einstein was good, but not great.
it was tensor calculus. Okay, it's not for the weak-hearted. And so it turned out it didn't happen. But in the interim, Leverrier passed away, securing the knowledge that he discovered 2 planets. But people were still looking for it as late as the turn of the 20th century. It's soon into the 20th century. They used to announce days where you could look for a planet crossing the disk when it was predicted, and Scientific American published them. They stopped doing that about this time because there was no need for it. It was understood that this was a swing and a miss by Leverrier. Okay, what about the search for Planet X? Back when, in the dark old days, when Pluto was still considered a major planet, it was noticed that Neptune was doing the same shenanigans. Neptune was not where it was supposed to be, very precisely. And so people started looking the way Leverrier and Adams thought, whoop, why is it doing that? Must be something built in the slide to tell it to go automatically. And
No, through slide deck precessing.
yes, the slide deck is precessing. Kepler's third law is pretty straightforward. So using nothing more than Newton's laws of gravity, that all masses attract each other. There's a slight gravitational attraction between myself and everybody else in the room. It's not very much. Interestingly, the guy who did the experiments that put numbers behind the strength of gravity was an experimentalist named Utvash, and he was even bigger than me. And he disturbed his own experiment. He had to leave the room, let the experiment settle down when he was measuring the strength of gravity. So it's not a complete joke, that I have a gravity well and I just don't attract moons or anything. But you have to know simply 2 things to get the mass of, in this example here, of the sun. You need to know the time it takes for a planet to go around and the distance between the planet and the star. And you get the mass of the star. This is Kepler's third law. It's how we know the mass of everything in the universe. It's how we know the mass of our galaxy. It's how we know the mass of galaxies themselves. It's how we know the mass of galaxy clusters. It is by applying a version of Kepler's third law. And it works with planets and their moons. If we look at moons going around planets, we know how far away they are, then we can say what the distance between them is, and you just measure the time it takes to go around and its distance, and you get the mass of that planet. Problem is that with planets like Uranus and Neptune, we have lots of moons. They're also very far away. And precisely measuring their positions and the time when they're in a particular position in their orbit is more difficult than we'd like to let on. If the planet doesn't have a moon, you have to be clever like a human being and create your own, what we call those satellites. So when shooting a satellite past a planet and watching how it deviates in its orbit, how it's attracted to that planet, you can get the mass of that planet. Because the mass of the planet is huge compared to this tiny little spacecraft. You don't really care about the gravity of the spacecraft, right? It's like me, in terms of, it's true, the Earth and I pull on each other with the same force. But my force is very, very tiny compared with the mass of the Earth. And so my mass is very small. We don't care about that, even though we have the same force. And so it's time to do the experiment and send a planetary probe out past Neptune and see what might be there. And so we're looking for the 10th planet because Pluto was considered planet number 9. It was called Planet X. It's sort of a play on the Roman numeral X for 10. It turns out, though, that it doesn't exist. That information was not available until the late 1980s. In fact, 1989, when Voyager 2 went past Neptune and precisely measured its gravity, as opposed to just sort of a little dart throw. This was very precise. And then the need for another planet perturbing Neptune in its orbit simply evaporated. And so there were an awful lot of us, not a lot of astronomers. There were more than 1 or 2 astronomers who spent their careers on this wild goose chase, trying to track down a planet that didn't exist, and in fact doesn't exist. There isn't an astronomer alive that hasn't looked at the database of something like the IRAS satellite that looked in the infrared and looked for warm moving objects, right? And it's not there. It doesn't exist. So we relied on Voyager 2. Voyager 1 got nowhere near Uranus and Neptune, but through a fate and some really good engineering, Voyager 1 started to fail on its approach to Saturn, and it was fixed in time and managed to get the data. And by the time it got there and looked through the data, they were supposed to be looking at its moon Titan. Turns out there's nothing to be seen. It's in a cocoon of optically opaque gas. And Voyager 1 hadn't been fixed. Voyager 2 would have been sent on this goose chase to go past Titan and take a look. And it would have been lost. The opportunity is lost to go to Uranus and Neptune. And so the engineers that worked on this project, most of them have retired now. Some of them passed on. These satellites have been, have been functioning now for nearly 48 years, and they're still sending data back. But the most important data, in my view, was the information on the gravity wells of Uranus and Neptune. So here's a schematic. NASA is so, I don't know what's the word I want to use. Persnickety? I don't know. The stars in the background are real. Most patterns are real. They're not just random. So the third rock is the blue one. That's the Earth. And it launches Voyager 1 and Voyager 2, who go past Jupiter and just traveling a little behind it, pick up a little speed. Voyager 1 goes off in some other direction, and its mission in terms of planetary exploration is over. Voyager 2 goes on to Uranus, pulls the same trick, and is vectored from somebody at a desk in Pasadena.
Some good math there.
Good math, within a few thousand miles of its target at Neptune, and sent back those beautiful pictures that I just showed you. The planets become in this alignment, to be able to do this trick about every 175 years. In 1978, when this mission was launched, the previous time that the planets were in that sort of alignment, Thomas Jefferson was president, and Lewis and Clark were trudging around trying to find the Northwest Passage. And so they're very rare. We're finding better ways to get around the solar system now. But this was quite fortuitous.
Slingshots, just a direct flight to Neptune probably takes a lot longer.
So they don't, I kind of always assumed that they would do at least one full spin.
Oh, no,
They just
no,
whip
they just, it's a flyby. They're going far too fast to be captured by their by that planet's gravity, and that's intended. If it was moving any slower, it would take 50 years just to get out to Uranus, right? It would be forever. Well, these were flyby missions. They simply go, and they have a little bit of leeway in tuning the trajectory so that you can choose your targets. Maybe this moon is a bigger target and more interesting than this moon. You take on a gamble, nobody knows what they look like, so you're just going to try it. Yep.
That's like a thing.
Yeah, see, I think I've always pictured it like a sling.
And we're like putting on a green and
You're riding a.
riding
Right.
around hole.
That's right. Except
Except the steel energy.
That's right. You don't.
That hole
if-
is that hole moving.
Yeah,
so
yeah,
you're
that's
getting
right.
that.
The hole is
The
moving.
whole, the hill, the slope is moving.
Right.
And now you're.
Yeah.
Lining up ahead of the moving of the slope. Slope moves in.
You-
Pick up something and pick up something.
If you want to pick up speed, you have to aim behind the planet. Interestingly, this just as an aside, this interstellar comet that's coming through is going to get quite a butt kicking from Jupiter on its way out. It's going to pick up some speed. Well, anyway, look at these stats on Uranus and Neptune. All of this information, this detailed information, comes from Voyager 2. It's not available any other way. And look at the masses down in the lower left. 4 significant figures of mass compared with the Earth's mass. And so now this is precision astronomy, and the need for a perturbing object pulling Neptune and tugging on Neptune is unnecessary, just simply evaporated with Voyager 2. And the people that spent time looking for Planet X were really wasting their time. But that's retrospect, that's hindsight.
Was there, do I remember correctly, what was it, maybe a year ago, that one of the Voyager craft sent back very unexpectedly some a reaction to something and nobody really.
I don't know that there was anything unexpected. I think Voyager 2 had something of a computer malfunction that had to be dealt with.
I had to reset the abacus.
The abacus, right? They had the little rat that does the abacus back and forth had to be given some more cheese. These are very, very, it must have built in, I made these slides and the built-in default is to advance, and that's really irritating. Nobody asked for that. Who asked for that? Not me. All right. So comets are these things that are best described as dirty snowballs. They're bits of dirt and rock held together by various ices. Ice of methane, ice of ammonia, but almost all of it is water. It's water ice. And so we have this design here of this comet that we've seen up close. This is also a flyby mission where it appears to be it looks like a bowling pin to me, but it's bilobal. We got this thing here, and it's kind of attached to this thing here. And this very smooth area, which is just filled in with the loose dirt, I suppose. And you see stuff coming out. So what happens is the side, when it gets close to the sun, the ices start to sublimate. They don't melt and become liquid. They just go directly to gas and release the gas and the dust. And so you end up with 2 kinds of tails. This is a gas tail. Almost all of the molecules glowing in the blue here were once water molecules, and they've been split apart by ultraviolet light in the sun. And this part of the tail is dust particles. These are simply this is simply reflected sunlight. If the camera was color calibrated, it would look just like the sun. They're actually quite black. They're much darker than the moon, which reflects, depending, 10 or 15% of the light. This is more like 3 or 4%. It's darker than freshly laid asphalt. They're really, really black. It's soot, right? So it's carbon soot. So here we have Lexington. Campus is over here somewhere, Red Mile. This is New Circle. This is Man of War Drive. And if we overlay this particular comet over the top, comet 67P, you can see that it's about 4 kilometers, about the distance from downtown out to New Circle, out to the out past the mall. P just stands for periodic. It's a well-known orbit, and it repeats it's in the Jupiter family. It must have a period of 5 years or 7 years or something like that. And this time, European Space Agency sent a probe that did go into orbit around the comet and stayed there for the better part of a year. In fact, it was sent out to begin its mission before it got too close to the sun and started erupting material, and then followed it around the sun and then back out again. And so it's safe to say we know more about this comet than we know about any other comet in the known cosmos. Now, this has nothing to do with anything. I just thought it was interesting. One of the lobes, that bilobal comet, is, to me, just looks just like Half Dome in Yosemite. They're about the same height, and so on. On the right, on Earth, you accelerate for about the first 5 seconds or so, and then you stop because there's air friction, and you slow down and you move at the same velocity. It would take the total time roughly to get to the bottom, 22 seconds, after which then you should have all of your affairs wrapped up before you hit that bottom. On the comet, the acceleration due to gravity, there's no air to stop you from falling. It's about 1 millimeter per second, which means after the first second, you're moving 1 millimeter per second. Millimeter is about the thickness of your fingernail. After the second, you're moving at 2 millimeters per second, 3 seconds, 3 millimeters per second, and that does not stop. It's exponential because there's no air to slow you down. It's just possible that if you didn't hit a boulder on the way down, you could do that jump, land in that what looks like soft sand. I don't know. No one knows what's under there, and survive it. And I'm going to pass this around. This is for those of you if there's somebody looking, this is the model that I made. It's bilobal, and from the pictures, you do not get the impression that it looks like a rubber duck, but it does. It looks very much like a rubber duck.
A lot of comets they actually find have this.
Yeah,
This bilobal appearance, and I don't know that they really expected that.
No, that was unexpected. This bilobal thing is another scandal. We need to understand that. It gets worse. It gets worse.
Didn't you do one of these lectures on, when you did that, you talked about how comets tend to be bilobal like that?
It's a common theme on the hit parade. I wouldn't say it's the two. The problem is, how do you get two comets to stick together without destroying themselves? That's the issue. Afterwards, there's a model up here of Voyager 2, if you wish to take a look at it. This is the magnetometer. It's just a loop of wire, measures the magnetic field. It just pulls out. So if you pull that out, don't panic. This is the camera arm, and this is the generator where the plutonium sits to keep the plutonium as far away from the electronics in the machine. The dish is about 14 feet across. So this was I think these may have been the first satellites that were not spin stabilized, that they were stabilized by little bursts of gas to keep them moving in the same direction. So if the main constituent of water, this is a cartoon version of what water looks like. To be hydrogen, by the way, I asked a question of ChatGPT this afternoon about how tritium decays, and it gave me an absolutely wrong answer. I mean, it was so bad it wasn't even wrong. You really do need to be careful about that. Hydrogen is the simplest atoms you can have. It's a proton with an electron going around it, and that's all there is. What makes oxygen is there are 8 protons in the nucleus. You can have various numbers of neutrons. We call those isotopes. But if it had a different number of protons, it wouldn't be oxygen anymore. It'd be something else. Well, it turns out there's 3 ways you can make hydrogen. The normal sort of hydrogen, the stuff that you see in blimps that blow up and things like that. It's just normal hydrogen, 1 proton and 1 electron. There's a version of heavy hydrogen called deuterium. It has a neutron in it, so it's roughly twice the mass. Still only one electron because the neutron has no electrical charge. If it had a different number of protons, it wouldn't be hydrogen anymore, it'd be something else. And then there's tritium with 2 neutrons. We discount tritium because it's radioactive and it's just not around very long, and so we don't care about that. We're not going to find any tritium in a comet, in the water in a comet. But the ratios of how much deuterium you have to normal hydrogen tells you something about where that atom was cooked up, and they're distinctive. And then when you look at the ratios of the isotopes of hydrogen and oxygen, you start to get a feel for being able to say, where did this molecule begin? Where in the solar nebula? How close to the central heat source was it when these nuclei came together? And so it's very important way. And so the question is, where did the Earth get all of its water? For more decades than I care to admit, I've been telling students that the water on the Earth came from comets. Why not? Where else is it going to come from? Comets is the only thing in the solar system we know of, except for moons like Europa, which turn out to be mostly water. But how did they get to the Earth? Well, trillions of comets over billions of years left us with oceans. And if you took all the water and all the oceans of the Earth and brought it together, you would get a little drop, a drop about that size. And we know very well what the isotope ratios are in water on the Earth. Now, for several months, this satellite called Rosetta was in orbit around this binary comet, 67P, and sampled the water coming out of this lobe and the water coming out of this lobe. Anybody want to guess what happened? All 3 of these sources of water are different. So the water in the Earth did not come from comets like this. Where did it come from? Nobody knows. This is a scandal. This could have been titled "Scandals in Astronomy" through the centuries, because this is a scandal that we don't know this. And that's right. That's right. Somebody left the tap running, and we end up with it. So this comet lobe and this comet were certainly formed in the solar nebula at the beginning in different places. Now, how you get together at orbital velocities and just kiss together and stick without destroying each other is beyond me. This requires an explanation, a deeper one than I'm likely to come up with. And so this is really a hot topic for research. It's not cheap. We have the technology now. We have a rocket drive called an ion drive that can deposit you into orbit around one object and then go on after study to another object. And I imagine a probe, something with that sort of engine, will be the next one to go around. The comets, I mean, for the purposes of research, are pretty rare. I mean, just finding one that you can go from here and then over to here and planning that would seem to me quite daunting. In the real life, of course, comets are everywhere. They're just they're icebergs of the ocean, right? Like icebergs in the ocean. They're just frozen things flying around. And you really don't want to get one in your way, and you really don't want to be hit by a large one.
There's even 2 comets hitting each other, much less at a velocity low enough for them to stick.
Right.
Would have
Yeah.
astronomically
Right.
rare event.
But
But yet we keep finding these things.
that's right. Space is very big. As I'm quoting Douglas Adams directly now. Space is very, very mind-bogglingly big. If you think it's a long way down to the apothecary, space is really much bigger than that. And how these little tiny things, a few miles across, manage to collide seems very, very unlikely. The Earth, yeah, it's got a bigger. These aren't to scale, of course. I mean, the comet is just. I just showed you. It's would fit well inside Near Circle Road. So there's 2 objects that small, the chance of finding each other in the night, like 2 ships in the night, strangers in the night, I don't think that would be very likely. And yet we see this pattern over and over again. And it's weird. It's just weird.
Yet they can prove they came from way different places.
They
They
came.
weren't born like that.
They weren't born that way, not like Lady Gaga says they were. So there is another book on the discovery of Neptune that's updated. And I suppose I should read that. The second author, Paolo, and I don't even, is Italian. Anybody speak Italian? I'm just going to go with Maffei. He's passed on now, but he was a serious astronomer and a very good educator, apparently. He wrote 3 books. The second one of which, and the third one of which I'm not sure, is Monsters in the Sky. And basically, things lurking in the night sky that could be dangerous, comets, supernovae, runaway stars, things like that, that are interesting. Now, all 3 of these books are very easy to read, and they're quite informative. They're fun, very fun to read. However, he did write them in 1960. Some of his ideas are subject to revision. But nonetheless, they're really nice to read. And this story of Leverrier and the search for the planet Vulcan takes up 11 pages in this book. And so I severely cut down the, it almost became, while you're reading this chapter about the discovery, the supposition that there is another planet there named Vulcan, you really want to cue the Benny Hill music in the background, because it's what it seems like astronomers running everywhere with that silly music running, because it just got out of control, and lots of people spent a lot of time looking for this thing that didn't exist. I'm not saying that was unprofitable to do. You certainly ruled out, by surveying the environment around the sun, we certainly ruled out any sort of decent sized object within the orbit of Mercury, closer to the sun. It simply can't exist because we've observed it too closely. But I can recommend both of those. My guess is that the follow-on of the discovery of Neptune is, I think it's called Report on the Discovery of Neptune. It was published far more recently. And my guess is it may clear away some of the fiction, some of the stories for the real facts. Science is hard, people. Science is really hard. Any questions?
Mafi's famous for 2 big galaxies in the sky.
That's right. Maffei discovered. Yeah, but Maffei found those 2. There are 2 companion galaxies to the Milky Way. And if they were on our side of the Milky Way, they'd be really, really conspicuous. You'd look up and say, wow, that's really cool. But in fact, they're on the other side of the galaxy, which is just stuffed with dust and you can't see it. And he was looking in the infrared. He was one of the pioneers in infrared astronomy and was looking with infrared wide field telescopes and found these 2 things.
They'd be showpiece objects in the sky if they weren't blocked by all that dust.
Yeah, if they were on our side of the galaxy instead of loitering around on the other side, it would be quite spectacular.
We'll swing around there eventually, right?
Yeah, so the sun goes around the galaxy every 220 million years, something like that. So I think you're still going to have to look through the disk, and
yeah, less stuff, but still stuff.
Yeah, it's unfortunate. The only obvious little companion galaxies, dwarf galaxies, are in the southern hemisphere. You can't see them from here. Alas. Okay, well, thank you. I think we should end it here. I think I just hit stop share, right?
Yeah.
Okay.
Those books are pretty cool. Can you find those online?
You can always find these online. Sometimes you can find them in half-price books. What I would do, used books appear on Amazon, but if you know it's out of print, the first place you go to is ABE Books.
Okay.
And look for them there. That's just a invaluable resource. But I mean, half-price books too. Half-price books, their website is a mess. It's just horrible. But if you go to one of the stores in town, there's 2 in town,
yeah,
and say, I'm looking for these books, will you check the other half-price books in the state? If they find it within the state, they'll ship it to their store for free, which is really kind of nice.
Thank you.
Okay, any other? No, you're welcome. How'd I do on time? Not too bad. Not too bad. Yeah, the Voyager, you may have guessed I bought a 3D printer a few months ago and I'm spending way too much fun time with that thing.
Like both of these? No.
Yeah,
Printed both of them?
yeah,
That's
I've got a model of the moon in my office that's about as big as I can print. It's about this big, 20